In this mini video, we present a way to reconstruct hidden patterns using L-directional associative memories. The starting point is the classical Hopfield model, where a recurrent network stores patterns as attractors of its dynamics. Here, we couple several Hopfield layers, sharing the same Hebbian matrix. Within each layer, standard Hebbian couplings promote retrieval, while between layers, anti-imitative couplings push different layers not to fall into the same attractor. The objective is a multi-channel machine that can disentangle noisy mixture and recover the underlying patterns. We consider not just one, but L-coupled Hopfield networks, all running in parallel. Each layer hosts its own configuration of spins and can retrieve a different stored pattern. Inside every layer, neurons interact through the same correlation matrix of the stored patterns. This ensures that each layer behaves as an associative memory. Layers are coupled to each other through anti-imitative couplings. This penalizes configuration where different layers stay on the same patterns, promoting specialization and pushing different layers to retrieve different patterns. On top of the couplings, we allow for external fields acting on each layer, which can encode prior information or weak hints about the pattern to be reconstructed. The combined effect is that layers cooperate to split the workload. In such a way, the network performs parallel retrieval of multiple patterns from mixed or noisy inputs. At each step, all neurons in all layers are updated in parallel according to the sign of the total input field plus thermal noise. Within each layer, the total field acting on a neuron contains the usual Hopfield contribution, making every layer behave like an associative memory, pulling the configuration toward one of the stored patterns. On top of this, each neuron also feels a contribution coming from other layers. These intralayer fields are anti-imitative. They penalize situations in which two or more layers attempt to retrieve the same pattern. After iterating the dynamics, each layer settles into a spin configuration, which is interpreted as a candidate pattern. The input data for the algorithm is the pattern correlation matrix, even though the patterns themselves are unknown, and a set of mixed combinations. The procedure depends on a small set of hyperparameters: the inverse temperature, the interlayer coupling strength, tanning how strongly layers repel each other when they're trying to retrieve the same pattern, and external field strength. For each spurious combination, we run the dynamics until convergence, thus producing L candidate patterns. After reconstruction is done, we apply quick checks to remove obvious duplicates and discard clearly unstable or low-quality configurations. Thanks to anti-imitative coupling, the layers do not all fall into the same attractor. Instead, they tend to spread over different patterns while being driven by the same mixed input. Repeating this procedure over many different mixtures, the machine performs parallel reconstruction. From a cloud of spurious combination, it gradually assembles a library of distinct candidate resources. The acceptance criterion works as follows. We cluster candidates by their mutual overlaps, keeping one representative per cluster, and test them using the pseudo-inverse matrix to assess its quality. Only those behaving as genuine patterns are retained. We finally test the model on random mixtures of hidden patterns, measuring both how many patterns are recovered and how well. Increasing the number of layers, the machine reconstructs more hidden patterns from the same pool of input mixtures, and the critical load shifts to larger system sizes. When a pattern is recovered, it is typically very accurate. The overlap with the true pattern is sharply concentrated near one. Thus, larger L boosts capacity while preserving high reconstruction quality. More information can be found on the archive paper. Thank you very much for your attention.